All right. So greetings, YouTube. Beautiful mind here. So let's see. So we're continuing chapter 2 on our exploration of exponential and log functions with section 2.4, a few applications, uninhibited and limited growth models, and some objectives here. We want to find functions that satisfy the dp by dt equal to kt and solve application problems using exponential growth and limited growth models. Okay. So we have this theorem that says that a function y equals f of x satisfies this equation, dy by dx equals kt, or f prime equals k times the function, if and only if y equals ce to the kx, or f of x equals ce to the kx for some constant c. So like if we were to differentiate here, c is a constant, right? So then it's going to be, it should be c, let me think about it, c times e to the kx times k. What am I missing? K times y. I'm just curious as to where did the c go, the constant. This times that derivative. Okay. We'll see how it evolves. Let's see. So find the general form of the function that satisfies this equation. The derivative of some function with respect to t equals 5a. So then the function has to be of this form, right? Let's see. If we take the derivative with respect to t, it's basically, it should be like a repeat of this times 5. What am I missing? Let's see. So, okay, let's look at this one. So it says the function n equals ce equals this, where c is an arbitrary constant. As a check, note that n prime of this is going to be k times this. Oh, okay. I found out. It finally dawned on me what I was missing, right? It's because I wasn't writing it out, right? So right here, what we're saying is correct. It's k times the function, and this is the function n, right? So we just weren't doing the substitution. That's what we were missing. So that we were doing like 5 times this thing, and we weren't just replacing this thing by a, right? Okay, I was like, what am I missing? It had to dawn on me. Okay. Anyway, so what we were saying is fine, so we can keep moving. It was going to irk me until I figured out what I was missing. So this equation, so k times the original function, so p prime equals k times the original function, is the basic model of uninhibited or unrestrained population growth. But the population is comprised of humans, bacteria, and a culture, or dollars invested with interest compounded continuously. Continuous exponential growth. Where C is the initial population, where C is the initial population. So where C and T is the time. Oh, where C is the initial population, P naught. Okay, that's fine. Yeah. So in this example, suppose that some amount P naught in dollars is invested into a saving account where the interest is compounded continuously at 7% per year, and the balance P grows at the rate of dp by dt equals 0.07 times the original function. Find the function that satisfies this equation and write it in terms of P naught and 0.07. So then what, P of t, so we can just use the theorem directly, right? So exponential growth, I usually use like per PE to the RT, so the P naught, E, the rate in this case is 0.7 times t. And then, if we took the derivative, it's going to be this entire thing times 0.7, so then it confirms basically the whole substitution thing like we discussed before. Then part B asks us to say we have 10,000 is invested. What's the balance after 1 year? So now we can use this formula. Our initial amount is 10,000. 1 year is there, and then use a calculator to crunch this number. And then C asks us if 10,000 is invested, how fast is the balance growing at 1 year? So find the rate of change. So P prime, right? So here's P. P prime is this guy. So then let T be 1, and we'll get this result. Okay. I know I kind of glossed over that. I'm gonna just let that be. We'll get some practice once we get into like class time. We'll be working on homework. Ooh, my battery's getting low. We'll get practice with this kind of stuff. Okay. The world population was approximately 6 billion at the beginning of 2000. It has been estimated the population is growing exponentially at a rate of 0.016 or 1.6% per year. So the rate of growth is going to be 0.016 times P, where T is the time in years after 2000. Find a function that satisfies this equation. Find a function that satisfies the equation. Assume that the starting amount is this, and we have this. Let me see. Okay, so I mean, I can't shake this feeling. What I usually do, like if I'm doing PERT, right? So P of T, P naught, I usually do e to the kt. I think this should be fine. Let me kind of take this onto the next page. Okay. Okay, so that's just a direct use of the theorem, and we can confirm by taking the derivative. So then we should have P of T is going to be P naught, which is 6.04 e to the 0.016 times T. If we were to take the derivative, 0.16 times P is correct, right? Okay, so that should be the first one. The second one, estimate the world population at the beginning of 2020. So when T is 20, so then for B, it should be P of 20, 6.04 e to the power of 0.016 times 20. And then I'm just going to say calculator. I'm not going to do that right now. Yeah, we can do it. We got it. It's because I just have to open up another window. I'm just being a little lazy. All right, and I know you can't see it. I'm just going to crunch the number. So then I'm going to do 6.04 times e to the power of 0.016 times 20. Okay. So I don't know if this still holds with this whole COVID thing going on. And it says the estimated world population. Who knows what effect COVID is having on the world population? Okay. So this is approximately 8 point. How many decimal places they did? They did 4, 3, 1. Let's do 3179. 3179 people. Okay. Okay. And then for C, rate of change, right? So then P prime, basically we're looking for P prime of 20. P prime is going to be, it should be the 0.016 times P of 20. So we're going to take that answer and multiply some, I was going to say times 0.016. So it should be, at that moment, the population should be growing at a rate of 13 point, I'm going to do 3086%. Okay. See how do we do? So we got the 6.04 e to the there, and then 8.3179 billion people. Okay, that's fine. And then per year. I think that's fine. I think what we have is okay. Okay, I'm going to let that be. All right. So then we have this logistic equation, right? So this is a logistic growth model. It kind of, the graph looks like, it starts off exponentially and then it ends logistically like a log function. This is a model for population growth and where there are factors preventing the population from exceeding some limit value L, perhaps a limitation of food, living space, or other natural resources. So instead of the population growing exponentially, it'll start off exponentially, then it'll capsize. It'll reach a cap, something like this, right? So it'll start off exponentially, and then it'll reach a cap. So spread by skin-to-skin contact or via shared towels or clothing, mycelium, I don't know, resin, MRSA, can easily spread a staph infection through a university. Left unchecked, the number of cases of MRSA on a university campus 2 weeks after the first cases occurs can be modeled by this logistic growth model. Okay. Find the number of weeks of infected students after 3 weeks, 40 weeks, 80 weeks. Find the rate at which the disease is spreading after 20 weeks. Explain why an uninhibited growth model is inappropriate, but a logistic equation is appropriate for the situation. Then use a calculator to graph. So for the first one, we would just plug in those values in the calculator. Let me see. T weeks, right? So this is already in units of weeks. So we would just plug those different values in. Find the rate at which the degrees is spreading. So it looks like we take the derivative, right? We could either do the quotient rule or rewrite it as a negative exponent and use the chain rule. I'm just going to kind of piggyback on what they have for the sake of time, even though we got a good amount of time. And then, so I'm just piggybacking on what they have. Explain why an uninhibited growth model is inappropriate, but a logistic equation, because you have limitations on the spread, right? If we're talking about the spread of the campus, what could be some of the limitations, like population size, right? Maybe, it's not going to go off to infinity. It's eventually going to level off. The biggest one I see is like the student size or the population size of the campus. So we just plug those in for the first one. Use your calculator. You should be able to confirm those. I'm going to let those be. So, did I do n prime wrong? What did I say? Yeah. Find the derivative, right? Okay. Yeah. See, I just didn't feel like doing all this. So it looks like they did low D high minus high D low over low low. So I'm going to let you kind of work to that. Once you have the derivative, then let T be 20. And so after 20 weeks, the disease is spreading to the campus at a rate of about 4 new cases every week. Okay. So then unrestricted growth is inappropriate for modeling the situation because as more students become infected, fewer are left to be newly infected. So the logistic equation displays the rapid spread of the disease initially, as well as the slower growth rate in later weeks. Then there were fewer students left to be newly infected. Okay, that's kind of interesting. And then we have a graph that is going to look something like this. And that's it. So, I know it was a little bit, choppy or whatever, but we're going to kind of go with it for now. And be sure to write down your questions and just get them answered. You just have to bring them to me and we can talk about them. Okay. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.